Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 31 where we will be looking into the mobility model. Again, the reason for looking into mobility model is to extract the final value of the current. Now till now, if you remember, in all our discussions which we were doing in our previous lectures, we were assuming that the mobility is low field mobility and it is remaining constant independent of any bias or any other structural parameters. Now we will likely deep dive into the basics of mobility models and how they are depending on the electric field, on biases and various other effects, and specifically the scattering effect we will be looking into in a realms of cryogenic electronics. So the outline for this talk is we will look into various mobility models, strong inversion relationships with as far as mobility is concerned. We will look into Coulomb scattering and its mobility relationship, and then the dependence of mobility on inversion charge at low temperature. We will also look into inversion charge relationship, effective mobility and generalized mobility at all the intermediate models. So the end of this lecture, I will be having a generalized mobility model for large number of temperature range right from cryogenic to room temperature. So that mobility model, why will it be important? It will be important when you will be actually modeling the device. So if you know at what temperature you are, then you can fit in the value of temperature in the generalized mobility model and you can extract the value of mobility for that particular range. Once that is known, you can actually find out the total current flowing through the device because of that mobility which is happening. Now let me come one by one and explain to you. Now this is sort of a experimental data which has come out. So what is the mobility? Let me first of all tell you what is mobility. So if you look at the mobility concept, we know that the velocity of the charged particle, right? If there is if for example an electron, if you apply electric field to the electron, so if you have an electron here and if you apply, this is a negatively charged, if you apply an electric field in this direction, the electron will start moving in this direction with velocity v. So my velocity v will be given as minus e times small e, or e is the electronic charge, e is the electric field. This is the electric field, right, and this is my electronic charge, right. So these are the two factors which are there, electronic charge and electric field. Obviously, as you can see with the negative sign, because it is moving in the opposite direction. Now v is equals to, therefore v equals to mu into e, I am sorry, mu into e, right. This was the force actually, and this is mobility into electric field, which means that if you look the velocity, it is minus e times mu, where mu is the mobility of the charge carriers. So first thing, if you look at the dimension of mobility, it is meter square per volt second. This is the dimensionality which is there, dimension of mobility. Now if you look here, it effectively means that as the electric field goes on increasing, my velocity will go on increasing in a linear fashion, right. So therefore, let me just plot the velocity versus electric field graph and I will show it to you. So if you plot for silicon, if you plot electric field versus velocity, then it maintains a almost like a straight line here, but beyond a point it shows a constant value, which means that at this place the mobility is constant, right, independent of electric field. This place mobility is actually a field dependent mobility, and at this place, since the velocity saturation takes place, again the mobility is constant at this particular point. So we will go one by one and explain to you what these regions are. This particular place where there is a linear region of operation, where velocity and electric field are linear, they follow this trend, right, and therefore as you go on increasing the electric field, the force on the electron goes on increasing and the velocity is increasing in a fixed value, and therefore the acceleration of the particle is 0 in this case. The rate of change of velocity and electric field is exactly the same, and therefore if you find out this is v by e equals to mu, then if v increases by 10%, electric field increases by 10%, v also increases 10%, mobility remains constant. Please understand two things happening. As you increase the electric field, the velocity of the charge carriers increases, which means that now it encounters larger number of scattering places or lattice atoms per unit length. So if say for example you are moving in a small room, in a room and you are moving very slowly, then per unit time you will strike with the people sitting inside the room will be relatively small, whereas if you are moving very fast, then not only you are moving fast, the probability will increase, but also the number of people you will be colliding with will also be large. Exactly same thing happens for an electron in a lattice. So when you are actually increasing the electric field, the probability of scattering also increases. What means of scattering is that scattering tends to make your linear velocity go down and down. So there are two forces acting in it. One is the electric field which tries to move the particle in the forward direction or backward direction, and there is also a scattering phenomena which tries to move in the opposite direction of the electric field. Correct? These two are opposing forces. What happens is somewhere near here where the electric field is relatively large, the mobility becomes a function of electric field. Now the scattering starts to dominate over the force applied on the charged particle, and since the scattering dominates, its velocity tends to become smaller and smaller, and that is what is happening here. So the rate of increase is not there. So had there been no scattering, this would have actually gone like this. As you move further down, you see your velocity is becoming constant. Why velocity is becoming constant? Now the force which you are applying and the reverse scattering phenomena are exactly becoming equal. So velocity becomes constant, right, and your acceleration goes to 0, and you have a fixed velocity of charged particle. Exactly like you can do an analogous design with rainfall falling onto the earth, right. There is a critical velocity after which a constant velocity is reached. So this is the basic fundamental principle of any mobility model which you see, right. So what we look is we are looking into the scattering mechanism first of all. We are also looking into electrode mobility and hole mobility separately, and we are actually shifting from room temperature to liquid helium. Liquid helium temperature is what we are looking into, right, till about 77 K and 50 K and so on and so forth, and up to liquid helium means up to 4 Kelvin we are looking into. So on the y axis is basically my normalized mobility, right, and on the x axis I apply the potential electric field, right. Now as the electric field goes on increasing, first of all you see the mobility goes on decreasing. Very true, because as the electric field goes on increasing, the electrons will be more dragged toward the silicon dioxide interface, and therefore the scattering will be heavy, and therefore the mobility will reduce down, and therefore you see it is reducing down. Interesting point, as the temperature goes on reducing, the mobility starts to become larger and larger, right. That is what is happening, that as the temperature reduces, the scattering phenomena reduces, and for the same value of the applied potential bias, I get a much larger mobility. So the objective to study the mobility models are that it provides you a basic understanding of variation of mobility with bias in structure. Now, especially with cryogenics, we are not only interested into looking into the bias aspects of it, which means what value of voltage, drain voltage, source voltage, gate voltage you are putting, but we are also looking at the ambient temperature at which these models are working, right. The rule of thumb is lower it is, higher is the mobility. Now this helps me to develop a very accurate and comprehensive mobility model. So my final aim is to develop an accurate and comprehensive mobility model which will not be only field dependent, but also it will also depend on temperature, right. And therefore there are three major scattering phenomena which happens. They go on varying with temperature. One is known as Coulomb scattering. So when we have a Coulomb scattering, right, and these are purely electrical in nature. We have a phonon scattering, right. This is purely because of thermal issues in the system, and we have a surface roughness scattering. So three scattering phenomena comes into picture. Coulomb scattering is purely electrical in nature, right, and this is primarily Coulombic repulsive or attractive force between the charged particle and the lattice. Phonon is primarily to do with lattice emanating phonons, and they strike the particle, and therefore the particle shifts from its position. This is primarily to do with thermal. The last one is surface roughness. So your silicon dioxide interface, if it is not good, there are large number of roughnesses there. When I say roughness, it is basically material roughness, and at molecular level there are roughnesses of the charged particle. There also there will be scattering. So these three scattering primarily work, and we say that the low field mobility mu 0 is basically mu c plus 1 by mu ph plus 1 by mu sr, surface roughness, mobility and scattering, and therefore the overall mobility of charge carrier will always be less than the least. So if you have three phenomena which are there, out of the three phenomena, we will be concentrating in those mobility which is having the less, and overall mobility will always be less than the least, right. So the idea here is that these key scattering mechanism actually changes as we move in temperature domain. For example, phonon scattering almost goes to 0 at extremely low temperatures, right. And therefore, the overall mobility might be actually less than the phonon scattering limited mobility at low temperatures. Now, for example, if we look at T greater than 100 Kelvin for an N channel MOSFET, the effective mobility is given by this mu effective is equals to mu 0, which is this is known as the low field mobility. This is the low field mobility. E effective is the effective electric field in the transverse direction. This is the transverse direction electric field, and this is known as the critical electric field. So, when EC becomes equals to or E effective becomes equals to EC, my overall effective mobility is half the low field bulk mobility, right. And that is what you get, right. And also you can express mobility as 1 by mu effective equals to 1 by mu 0 plus gamma times E effective, where mu 0 0 is basically the low field mobility. Low field means zero field, when there is no electric field available and because of the external sources. EC is the critical electric field, gamma is a constant parameter whose dimensions are given, and that is independent of the applied voltage. So, it is basically a function of the material which you choose, and these occur for P channel for more than 20 Kelvin, and for N channel it is more than 300 Kelvin which you see. Now, the effective electric field, and this is quite interesting, the effective electric field is, so this is silicon dioxide, this is silicon. So, the effective electric field is directed in this direction, this is E effective, and it is given by this formula here which is shown here, is QD plus eta times QI by epsilon, right, where QD is basically the depletion charge and QI is the inversion charge, right. Eta is a constant parameter, right. It is, I will not go into details of it, but typically it is 1 by 2 or half for N channel and 1 by 3 for P channel. So, if you take an N channel device, my effective electric field will be given as QD plus 1 by 2 times QI divided by epsilon. It effectively means that the half of the inversion charge actually contributes towards the electric field in the transverse direction, right. And for a P channel, 1/3 of the holes contributes to the electric field in the transverse direction. Epsilon is of course the permittivity of the material. So, I get effective electric field as written as QD plus eta times QI by eta, right. QD is the depletion charge. So, what we do, we look at the total charge and we divide that by epsilon and we get Q, right, and that is how you define the overall effective electric field. There is another way of looking at it. Now, you see, when you apply a gate voltage, right, when you apply a gate voltage, out of the gate voltage, some of it is actually utilized to invert the channel, and that is referred to as the threshold voltage. So, therefore, the effective voltage seen at the silicon dioxide interface is actually Vg minus Vt. So, I will explain to you what do I mean by that. So, I have this interface here, I apply a voltage here Vg S, out of which to invert the channel I spend Vt. So, the effective amount of voltage seen at the interface of silicon dioxide and silicon is actually Vg minus Vt, and that is the reason you see that mu effective is given as mu 0 upon 1 plus theta times Vg minus Vt. Theta has a value of 1 by Vg, and Vg minus Vt is the effective voltage available at the input side. Now, if that is what is there, where mu 0 is basically the low field mobility, right, mu 0 is the low field mobility, and it is different from mu 0 0 because theta represents this theta represents the mobility attenuation factor. Higher the value, lower will be the effective field mobility, higher will be the attenuation, and Vg represents the gate voltage, Vt is the threshold voltage of the device, C oxide is of course the gate oxide capacitance. So, based on this equation, I can write down the inversion charge to be equals to C ox into Vg minus Vt, because Vg minus Vt is the effective voltage available to me. If I multiply that with oxide capacitance, I will get the inversion charge available to me. So, if I have a strong inversion, how does the mobility behave? Weak inversion, how does the mobility behave? That we need to find out. Now, let us look at the strong inversion mobility model. The mobility at strong inversion is given by this complex formula here, where EC is my critical field, mu 0 0 is at zero electric field, EC is the critical electric field and Q is the depletion charge. Now, you see quite interestingly here Qi does not play a major role, and this is what is known as a screening effect which happens. Why? Because you have a depletion region which is very strong, and therefore it screens the inversion layer charge, and therefore the effective mobility only depends on the value of the critical field and also on the depletion charge. So the attenuation factor, again experimentally and numerically determined, is given by eta times Cox upon EC epsilon plus Qd, equation number 6. So the alternative mobility models which are available to us, even in strong inversion and weak inversion, is given by these equation number 7 and 8. Please see that the theta factor, which is basically the mobility attenuation factor or the degradation factor, is directly dependent on the value of Cox, right. And if you remember, Cox is primarily is equals to epsilon ox by Tox. Epsilon ox is the oxide layer permittivity divided by the thickness of the oxide layer. So if you make your thickness of the oxide layer go smaller and smaller, and this is, please carefully listen to this. If you are lowering your oxide thickness smaller and smaller, you tend to make your Cox go larger and larger. When Cox becomes larger and larger, theta goes on becoming larger and larger, which implies that the reduction which will happen in the mobility will be also stronger, which means that if your oxide layer thickness is reduced, it adversely impacts the mobility and makes it go low. Physical reason, because as you reduce the oxide layer thickness, the electric field in the transverse direction reduces, which ideally makes the mobility go to a low value. Now let me come to the strong inversion mobility model. There is a dependency of mobility parameters mu 0 and theta is already there with respect to Qd, where Qd is the depletion charge. You need to also understand that when Qd equals to 0, when the depletion charge is actually equals to 0, right, this obviously does not happen, as I discussed with you. They will never generally occur in real devices when Qd equals to 0. Then we refer to mu 0 as the zero field mobility at the place where Qd equals to 0. Again, this is a sort of an extrapolation, it is not the actual sense which you will see. So in the case of strong inversion, the absolute depletion region can be expressed in this manner, and it depends upon the value of Vb as well. N doping is the doping concentration, phi f is the absolute value of the Fermi potential, and Vb is the potential which you apply. And you see the charge is actually a non-linear dependency on the voltage, a substrate bias, right. As the substrate bias goes on increasing, the charge actually increases in a non-linear fashion. Let us look at the Coulomb scattering and therefore the mobility relationship. I discussed already with you what is Coulomb scattering. The way we represent is in this manner, right. This is the equation which you see, 1 by mu 0 0 equals 1 by mu max plus chi times Qi, where mu 0 0 represents the mobility under the consideration of interface trap charges or interface charge effects, whereas mu max is the maximum mobility which you will actually see in idealized conditions, right. Chi is a proportionality factor, and Q of I is the interface trap charges which are responsible for the scattering phenomena. And interestingly, therefore 1 by mobility, which you find out 1 by mu 0 because of Coulomb scattering, will obviously depend upon not only on the value of chi, which is proportional to Coulomb scattering, but it will also importantly depend upon the value of Qi. Qi is the interface trap charges density which you see, and both these phenomena will make the mobility change drastically in a longer run. Now let me scale down the temperature to a low value, right, and see how it works out. The relationship governing this behavior is 1 by mu effective equals to A by Qi plus B plus Qi, right, and this is at temperatures for n channel, we will just concentrate on n channel, is somewhere below 40 Kelvin, right. A is a constant which depends upon the Coulomb scattering. B is again a parameter that depends upon surface roughness scattering, and Qi is the inversion charge, right. So you see, effectively, if the value of A and B are large, that can only happen when your mu effective is small, right. So therefore, higher the value of these parameters which reflect higher scattering will result in a lower mobility. So these equations are placed in such a manner that if values of A and B are large, then that results in mu effective to be relatively small. To a low value, it comes out to be a very low value, right. Okay. Now the relationship emphasizes that there is a dual contribution of both Coulombic and surface roughness scattering for the overall mobility behavior at low temperature. Now when we look into the let me quickly go through these slides and explain to you what the value are. So we have already looked into the inversion charge. We look into the maximum mobility is derived as square root of AB. So you see mu m is proportional to 1 by square root of AB. So, higher the value of AB, lower the value of mu m, which I have already designed for you. The effective mobility therefore at low temperature is given as 2 mu m upon Qi by Qm into Qm by Qy. Now, you see higher the inversion charge which you see, because you want more current, you end up having a lower value of effective mobility. If your inversion charge is larger, then you get a much larger this thing. So, if you look at the denominator here, and then this is Qm dot Qi, and this will be Qi square plus Qm square. This will be the denominator term. So, this will go to the top, and I will get 2 mu m times Qm dot Qi divided by Qi square plus Qm square. Now, you see if a small increase in Qm or Qi take place, since the denominator is a quadratic expression, the mobility fall will be much larger for inversion charge as well as mobile charges. This is under strong inversion condition, where the gate voltage is much larger than the threshold voltage of the device. I get mu effective to be equals to a quantity which is given by this equation 13, right. And therefore, we come to the two important takeaway from all this discussion, that the electric field in the transverse direction is quite critical in determining the value of mu effective, and the effective gate voltage, which is gate voltage minus the threshold voltage, is a effective parameter in determining the value of the effective mobility model, which takes into account all the scattering effect, Coulombic as well as phonon roughness scattering mobility model. This sort of gives you the generalized mobility model at intermediate temperature. When I say intermediate, I mean to say at cryo 10 to 20 Kelvin for P channel and 40 to 100 Kelvin for MOSFETs. So, for various regions of temperature range, you have various models available to us, and at T equals to 40 to 100 Kelvin, this is the model which has been given for both PMOS as well as for NMOS, correct. Now, N is a factor which varies from 2 to 3 depending upon where you are operating. Typically, higher the N value, higher will be the mobility. So, when you go to 300 Kelvin, the N value is typically large, and it goes down as you lower your temperature. Right. Possibly in my last slide, I will explain to you what the other effective mobility model are. This is under strong inversion again, but this is again in the intermediate. One equation which we get is this one. This is the major equation which we are referring to, where mu effective is given as depending upon the generalized mobility parameter B, and N should be greater than 2 and less than equal to 3 for all practical purposes. Now, if you look very carefully, and that is the reason, if you let us take you the most generalized condition of N equals to 2, the worst case scenario if we take, then this quantity goes to 0, and therefore, anything to the power 0 equals to 1, and this converts to 1 value. And if you make N equals to 3, then we get 2 times, you get 1 by 1 minus say 3. So, 2 to the power 1 by minus 1 by 2, right. So, it is 1 by root 2 which you get into mu m, that is the value which you get for mu g. So, it is basically, if you divide the overall mobility by 1.414, you will get the total change, right. And the Coulomb parameter A and B are experimentally determined by these two factors, right, where A and B are, this you can empirically find out the values of theta, C oxide and Ng, right. This is the final expression for Ug and theta for intermediate range, and this mu g and theta are in terms of A and B. A and B are already functions which have been defined to you here. This is A, this is B, and depending on A and B, we find the value of mu g and theta, right. So, A and B are very important parameters which depend upon the surface roughness scattering. Higher the surface roughness scattering, higher will be the value of A and B, and therefore, lower will be the value of mobility. The last point to be maintained here is that if there is any rise or there is a large increase in the Coulombic scattering, they will try to maintain the mu g by theta ratio constant. Why? Because mu g will, with higher scattering, theta will fall down and mu g will also fall down, so the ratio remains constant. What we have highlighted therefore is that the various factors, Coulomb, phonon and surface roughness scattering, are applicable at cryogenic temperature at various intermediate cryo, low cryo and higher cryo, and therefore, a generalized formula can be actually extracted from all these discussion, which I have already shown it to you in our previous slide. So, let me recapitulate about what we have done till now. I have explained to you the basic mobility model, right, and this mobility model dependency on surface roughness, on Coulomb and on phonon has also been shown to you, their respective equations have been discussed, right. We have also looked into intermediate mobility model, intermediate temperature mobility model, right, for T equals to between 100 and around 40 Kelvin, and this gives me a quite a substantial result which is very close to the experimental results available to us. We saw that there are two parameters A and B, and these parameters influence the mobility to a larger extent, and that gives me relatively. So for example, if the surface roughness becomes larger, value of A and B increases, and that reduces the value of the overall mobility. So by the end of this lecture, just looking at the expression of the mobility, you would now be able to plug this mobility model and place it in the current equation to get the overall current, such that the current is now depending on a mobility which is field dependent and temperature dependent, right. So by the end of this lecture, we will be able to extract the value of current given electric field, given substrate bias, given temperature, and given the structure of the device. So I hope you enjoyed this lecture. We will take care of the other parts in the next lecture. Till then, goodbye.